actually want to record on this computer. I tried recording my one this morning, first period, but sometimes it has a hard time seeing my webcam. So as I go back and forth, sometimes it's going to see it and sometimes it isn't. I found that in pre-calc when I was doing it. So I hope, and I never know whether it's going to take until after I check it. So I hope this takes. I'm starting out on this kind of view because if I start out on webcam, I got to just test it to see which one's going to work, honestly. It's kind of hit and miss. So anyway, I'm going to put my webcam on now and do the daily 2. Oops. Oh, that's because I had it off to the side for lunch. So here's a daily 2 number 1. All right. Which of these quantities are vector quantities? Okay. The vector quantities are the ones that have direction to it, and the ones are velocity, that has a direction to it. That can either be north, south, east, or west. Weight is always down, so that is a vector, and the other vector is acceleration. Okay. Distance is a scalar. Okay. Time is a scalar. Mass is a scalar. Now, there was a question this morning about distance versus displacement. I just want to see. I want to take a look at the responses for this. Yeah, there were, well, some people put displacement. That wasn't on the list, actually. But the most common incorrect answer here is distance. And I want to just make a little discussion about distance versus displacement. Okay. So I want to see what you're seeing. So let's start out here, and let's say I go 10 meters this way. Okay. And then I go 10 meters this way, 10 meters east, 10 meters north, and then 10 meters back to the west, and I end up here. Okay. Now the distance that I walked is 10 meters. My displacement is 10 meters north. Okay, so this is a displacement. And so displacement is a vector quantity. The distance that I walked is 30 meters. Now, instead, let's say I would walk this, 10 meters this way, 10 meters this way, and then 10 meters this way. Okay, 10 meters, 10 meters, 10 meters. Although the distance that I walked is the same as before, my displacement is very different. Now I'm 10 meters to the south. Okay, so distance is just the length of steps that you walked, the length of meters that you walked. The displacement is the difference between the initial position and the final position. Okay, so that's distance versus displacement. That's why distance is a scalar, while displacement is a vector. Okay. All right. Okay. Now the second one, if we have what it said was, the question was an applied force of 20 newtons is required to drag a box that weighs 50 newtons at constant velocity. At constant velocity. At constant velocity. Okay. I said that's important, and it does turn out to be important for a reason that I'll go over in a moment. It says, what is the force of friction? So what is the force of friction? Okay, and the force of friction. Okay, now the keywords at constant velocity. At constant velocity, I know that the net force is 0 because there's no acceleration. Okay, at constant velocity, the net force is 0. And since the net force is 0, I know that the applied force and the friction force are the same. They have to match up. Okay, so the applied force, if the net force is 0, that implies that the applied force is the same as the friction force, and so the friction force is 20 newtons. Okay, so those key words, at constant velocity. All right, that leads me to the net force being 0. That leads me to the forces in the horizontal must add to 0. Okay, and that's the daily 2 for today. Questions, comments? All right. Well, then I'd like to go over the multiple choice for the sample final exam. So if you would dig out the sample multiple choice, okay? Sample multiple choice. I'd like to go over these now, okay? Have until, I believe, 1:15. I don't know if it'll take that long or not. The first one, 4.73, can you guys see this? 4.73 centimeters is equal to how many meters? Okay. Well, according to the big Z, centimeters and meters, I have to move the decimal point 2 places, and centimeters was down here, and I'm remembering my big Z diagram. Meters was above, so I move it up, and so I move the decimal point to the left 2 places, and so my answer is 0.0473. All right, which was choice A, actually. All right, for number 2, a little scientific notation question. Okay, we're going to move the decimal point until we get a number between 1 and 10. So that's going to be 2.93. And then I moved to 3 places. Started out with a value of less than 1. 2.93 times 10 to the negative 3 is that one. For number 3, 45 kilometers per hour. And I want to convert that to meters per second. All right, so I got to eliminate the kilometers. So I'm going to cancel that out and change it to meters. All right, now the kilometers is gone. I got to eliminate the hours to minutes, and then minutes to seconds. There. And the only thing I have left in the top is meters. The only thing I have left on the bottom is seconds. There's 1,000 meters in a kilometer. 60 minutes in an hour, 60 seconds in a minute. And then I operate my calculator, okay? And if you do that successfully, you'll get an answer of 12.5. 12.5. And so that is the conversion, all right? Okay. Number 4. The shape of a graph for a direct relationship. Okay, well, another name for a direct relationship that can be used kind of interchangeably is a linear relationship. Okay, direct means linear, and therefore the shape of the graph is going to be a straight line. Okay, a straight line. Okay. So then we have number 5, and so use the following test from number 5 through 7. A ball is thrown straight up into the air. A ball is thrown straight up into the air, okay, with an initial velocity of positive 29.4 meters per second. Okay. Number 5 asks, at the top of the ball's motion up here, the acceleration of the ball. Okay, the acceleration of the ball is the same no matter where it is in the flight. The only force acting on it is gravity. Okay, so therefore, the acceleration is always the same, negative 9.8 meters per second squared, no matter where it is, okay? Whether it's on the way up, whether it's on the way down, or at the top. The acceleration is always negative 9.8 meters per second squared, okay? And I actually made a rather egregious mistake in my answer key for the true false number 10, where I said, if you look back on the true false, it says at the top of its motion when it's momentarily stopped, the ball on the previous side is accelerated negative 9.8. I marked that false in my answer key. That's an egregious mistake by me. That should have been true. Okay. And so I'm sorry, but that I gave you the wrong answer for that. It's such a key thing about physics. Okay. So sorry about that one. No matter where it is, immediately after release to the instant before it strikes the ground or strikes whatever. While it's in flight, no matter where it is, the acceleration is always the same. Gee, do you think I might ask a question on the final about that? Since I've been hammering on it for so long? Pretty good chance. Okay, so I certainly hope that you get that question correct on the final. Okay, number 6, the equation to use to determine the time of flight. Okay, so I want the time of flight. So I'm gonna make a little data table here. G, the time, the initial velocity I know is 29.4 meters per second, okay? I need one more piece of information, and remember we used that little trick, what really isn't a trick. We said at the top of its flight, for the first half, the final velocity is 0, or first half of the flight. And that means that I can use V sub f is equal to V sub I plus GT to answer this question, okay? And so that was choice B for that. And then for number 7, they actually want us to calculate the time. All right, so I need to just plug this stuff in here. So the final velocity is 0. I get 29.4 meters per second there. And then plus negative 9.8. Second squared times t. Bring the 29.4 over to the left side, and then divide each side by this. All right, everything cancels over there. Over here, I get the negative signs cancel. That's good because time's always positive. Get the meters canceling, one of the seconds cancels. And the seconds in the denominator of the denominator, that comes back on top, and turns out to be 3 seconds. Okay, however, that is not my answer. If you carefully read the question, what the question asks, or what the statement says, is the time of flight, okay? That implies the entire time of flight, not just the way up. And remember, this 3 seconds was considering the final velocity being 0, so that's the way up. Okay, 3 seconds to get to there. Well, it takes another 3 seconds to get down. So the total time then is 6 seconds. Okay, the total time of flight is 6 seconds. All right. Okay, that's numbers 5 through 7. All right, now number 8 talks about a distance time graph. So talk about a distance time graph. Distance time graph. So like D versus T. Let's say the distance is measured in meters and the time is measured in seconds. And I get something like this, some straight line of non-zero slope. And speaking of slope, because that's what number 8 says, the slope of a distance time. Slope is rise over run, a change in the distance over a change in time. Okay. Now, a change in distance over a change in time is velocity. So the slope will give you the velocity. Okay. All right. I have another way that I like to teach this also. Slope is rise over run. Yes. Rise over run. Well, the rise is measured in meters. The run is measured in seconds. And so the unit will be meters per second. And we know that meters per second is a unit of velocity. So this again indicates that the slope is a velocity. Okay. All right. Number 9 talks about a velocity time graph. So let's do the same kind of thing with velocity. Now, velocity is measured in meters per second, and time is measured in seconds. All right. So we can talk about slope again. And the slope, okay, the slope is delta V over delta T, okay? A change in the velocity over a change in time. But we know that's acceleration. Note once again, rise, you guys see this? Rise over run. let's just think about the units. The rise is measured in meters per second. The run is measured in seconds. And then meters per second over seconds is meters per second squared, which is once again a unit of acceleration. So another indicator. Okay. Now with these, with the velocity time, we can also take the area under the curve. Okay. Let's just talk about area. Area is one dimension times the other dimension, like length times width, right? So this will be measured in meters per second times seconds. That's measured in meters per second. The length, call it, and the width is measured in seconds. Multiply them together, and what do you get? You get meters, which is a unit of displacement. So the area under the curve of a velocity time graph indicates displacement. Okay. Now, number 9 actually says the area under the curve of a velocity time graph indicates displacement or distance. And that's choice A. All right. All right. Number 10. Bob puts his soda on the dashboard while he pays for his food. He forgets about it as he drives away. Soda falls into his lap. That's law of inertia. That's Newton's first law. Okay, the inertia of the soda kept it in the same place while the car moved forward underneath it. Soda ended up spilling out. So that's Newton's first law, law of inertia. Okay, okay. Number 11. So we have a box being dragged on the floor. So you have a box being dragged on the floor. 10 kilograms. It's at constant velocity. At constant velocity. I have a feeling that's going to be important. The applied force is 50 newtons. That's the applied force. Okay, number 11 says the net force on the box. I knew they were going to ask me that. At constant velocity, the net force is 0. The net force is 0. And so that's choice A. Okay. All right. Number 12, the normal force. They didn't really talk about the normal force very much. I should have taken it off of this sample test. Turns out that the normal force is the same as the weight. Okay. The normal force is the same as the weight. So you'd find the weight of 10 kilograms, which is 98 newtons. So that would be the normal force. There will be no questions about the normal force on the final exam. Okay, so I should have really just deleted this question from the sample final. What I probably should have substituted in instead is what is the force of friction? Okay, what is the force of friction? Okay, and if the net force is 0, that means that the force of friction would be 50 newtons. It would match the applied force. Okay, that's the thing that I was harping on in this year. Okay, I kind of let the normal force stuff go, but I didn't want to harp on that. I didn't want to emphasize that. Okay, number 13. If the force is increased to 80 newtons on the same surface, 80 newtons on the same surface. Okay, what is the acceleration of the box? Okay, what is the acceleration of the box? And let's see here. Yeah, I got to hustle it a little bit. So the if it's 80 newtons, then there's a net force now. Now there's a net force of 80 minus 50. 80 minus 50, and the net force is then 30 newtons. Okay? And then by Newton's second law, F net is equal to ma. That's going to lead me to the acceleration being the net force divided by the mass. Okay? The net force divided by the mass. And that will be 3 meters per second squared. F over m. Okay? All right, that's 11 through 13. Number 14, rocket problem. Mass, 100 kilograms. Okay, being propelled upward by a 2,000 Newton force. The net force on the rocket. Well, I have to consider the weight. Okay, and the weight is going to be equal to mg, right? And that's 100 kilograms times 9.8, or 980 newtons. So I have 980 newtons pulling down. I have 2,000 newtons pushing up. So therefore, the net force is their difference, or 1,020 newtons. Okay? Okay? 1,020 newtons. Okay. And then we have a concurrent forces problem. So I have 100 newtons at 90, and 240 newtons at 180. And I want the magnitude of the resultant. So I'm going to draw the resultant like that. Okay. The magnitude can be found by the Pythagorean theorem. Magnitude of r squared. And if you did that successfully, you would find the magnitude being equal to 260 newtons. Okay, 260. For number 16, it wants the equilibrant, the direction. Okay, the equilibrant was the vector that opposed this resultant. So I need this direction. Okay, I need that angle there. Okay, now for that, I'm going to use a tangent function. So the tangent of x is 240 opposite over 100. All right, and if I take the inverse tangent, I get 67 degrees. So the inverse tangent is 67 degrees. All right, I'm going to add that to 90. Add that to 90 so that the bearing of the resultant is 90 plus 67, which is 157. And then to get the equilibrant direction, I'm going to add 180 to that. I'm going to add 180 to that. And that will give us an answer of 337 degrees. And that's our result there. Okay. All right, and then finally, the very last one, a force has a magnitude of 20 newtons, and another force has a magnitude of 50 newtons. The resultant cannot have a magnitude. Okay, well, the most that they can have acting together is 70 newtons if they're pointed in the same direction. That's the max. The minimum is if they were acting in opposite directions. That would yield one of 30. That's the minimum. Okay. They cannot have a magnitude of 24. Letter A. Okay. They can have any value between 30 and 70, inclusive, depending on the angle between them, but they can never be 24. All right. And that's the sample final. The final that you'll be taking, it looks a lot like this. There'll be some true false, there'll be some multiple choice, and there will be some problems. Okay, it'll be a Google form. Do you have any questions for me? This is 5th period, so I think you'll be taking this on Thursday, right? Thursday, let's see, Thursday right in the morning at 8:30. All right. Okay, if you have any other questions, then feel free to attend office hours today, and I'll help you with it, or tomorrow, okay, or Wednesday actually. So best of luck on your tests. All right, I gotta let you go to your next class.